Now, regression is all about the relationship between our predictor variables and our response variable. And if we're going to do that, we first need to go back to the basics of just understanding the relationship between two variables. Does one variable move in the same direction as another? For example, as the number of customer complaints rises, does the number of refund requests also rise? Technically, regression does not assume causality, neither does correlation that we had seen in previous videos, meaning that one variable isn't necessarily causing the movement in the other variable. It may or it may not. And hopefully we'll have some either theoretical basis or we will have some intuitional knowledge that basically says that A leads to B. And so therefore if A moves up, B moves up or down. So what regression is measuring is how much of the movement of one variable occurs with the movement of another variable. And there are two types of relationships that we're going to be concerned with. Linear relationships, in which the movement is in a linear fashion. As one goes up, the other goes either up or down. And nonlinear relationships, which means that one may go up and the other may start upward and then tend downward as it heads towards a certain point. It's actually a curve, not a straight line. So a linear relationship between two variables is simply the notion that a straight line can represent the relationship adequately. Consider the graph that we have below. We have a number of refund requests and we have a number of complaints in a given day. So the refund requests are along the left and the x-axis is the number of complaints. As the number of complaints increases, our refund requests also increase. And we see all of the dots that represent that. The whole purpose of regression is to determine whether or not we can have a straight line go directly through all of these points so that we can get an estimate. Let's say, for example, if we have a number of complaints 20, we will get approximately 26 or 27 refund requests. Now, a nonlinear relationship between the two variables is the opposite of a linear one. It cannot be represented by a straight line. And the graph below represents this as a curve linear relationship. Now, it's a little hard to see, but if we have our dots that represent our points, we tried to draw a straight line through, which is that dashed red line. But what happens is that some of the points, especially towards the left and towards the very right, obviously are not being quite well represented by that dashed line. And we do have a green line here, which actually has a slight curve to it, and this line actually seems to do a better job in predicting the relationship between the two variables. So this is how you can tell the difference between a curved linear relationship, represented by the green line, and what would be a linear one, which would have been represented by the red line. Now, another concept we need is to know what an outlier is. So here we have a bunch of dots, and we have our regression line that represents this straight line that goes through all the dots. Some of these dots will either lie extremely high or extremely below this line, and we might consider these to be somewhat abnormal. Well, these are known as outliers. They're observations that don't fall within a normal range or a boundary of a data set. And so even though many times our data will look clean, we'll have one or two points that will definitely seem to be out of bounds, if you will. And outliers can be real. In other words, they are actually the true number that they're supposed to be. Or it can be caused by an improper collection of data. Say someone had said, well, my salary was $1, when in fact it was $100,000, but it was collected improperly. It can also occur through system corruption of data. It's up to the analyst to determine what to do with outliers, but there are a number of techniques that can handle them. Now, sometimes we'll have a situation where there's no relationship, where there's no discernible pattern between the x variable and the y variable. And clearly the graph below doesn't show any particular pattern. The numbers as x goes up, y remains somewhat constant. And in this case, we might actually even represent this with a straight line directly across. That's a special type of line, but there is no slope to it or there's no increase to it. It's just a flat line. And we say that there's no relationship between the two variables.